Welcome to Truth Behind History. Today we are diving into the High-Frequency Active Auroral Research Program, better known as HAARP. Let's set the stage. Picture the mid-20th century, when the Cold War turned science into a battlefield of brains. Superpowers weren't only racing for rockets and satellites, they were racing for information itself. Who could hear farther? Who could talk to submarines under polar ice? Who could watch the world without being seen? In that environment, a project like HAARP wasn't an oddity. It was a logical next step. Cold War military research created a simple but relentless incentive: stay a step ahead technologically, or risk falling behind geopolitically. That push produced a whole ecosystem of defense labs, contracts, and university partnerships. HAARP emerged from that ecosystem. Think of it as a specialized laboratory pointed upward, studying the ionosphere, the electrically charged region high above us. Why the ionosphere? Because it's the highway for certain radio waves. If you can understand that highway, maybe even nudge it slightly, you improve how messages and sensors travel across the planet. Now, interest in the ionosphere didn't start with HAARP. Since the 1950s, American researchers had been probing this layer for very practical reasons. Long before fiber optics wrapped the globe, high-frequency radio could bounce off the ionosphere and leap across oceans. Ships, aircraft, remote stations, even early warning systems depended on that bounce. But there was a catch. The ionosphere is alive. Sunlight charges it by day. Space weather rattles it. Geomagnetic storms can turn the best planned signal into static. So scientists asked a straightforward question: if we could measure those changes precisely, maybe even create tiny, controlled disturbances on purpose, could we predict and improve global communications and surveillance systems? In other words, could we make the unpredictable a little more manageable? Enter the institutions that built HAARP. You'll notice a familiar cast: the US Air Force and the Navy, both with obvious stakes in reliable, long-distance communication. DARPA, the agency designed to fund high-risk, high-reward ideas that might change the strategic game. And the University of Alaska Fairbanks, a scientific partner with the expertise and the location to study the high-latitude ionosphere, where auroras dance and space weather effects are particularly strong. It's a telling mix: military sponsors with strategic needs, a research arm built to push boundaries, and an academic institution bringing method and measurement. Each one had a reason to care, and when those reasons align, projects move from whiteboard to tundra. So what was the official mission? Communications enhancement. Not science fiction, not magical weather control, but the very down-to-earth goal of understanding how radio waves behave in a dynamic, charged sky. The idea was to transmit high-frequency signals upward, create small, temporary perturbations, and watch how the electron soup responds. Learn that, and you sharpen the tools that modern life quietly relies on. Think GPS accuracy for navigation and timing. Think more reliable radio transmission where satellites can't do all the work. Think mapping the ionosphere so a message sent today doesn't vanish tomorrow because the sun had a tantrum. If that sounds esoteric, here's an analogy. Imagine you're trying to hold a conversation across a canyon. Your voice bounces off the walls and sometimes comes back to you at the wrong time. Now imagine you could briefly clap, hear the echo pattern, and use that to tune your next sentence so it lands exactly where you want. HAARP is that carefully timed clap, except the canyon is the ionosphere, and the echoes carry ships' messages, aircraft signals, and timekeeping pulses that synchronize everything from financial networks to power grids. Of course, the Cold War context matters. When defense agencies fund research, the public inevitably asks, who benefits, and how much will be shared? Those are healthy questions. But on day one, the stated purpose was clearly scientific with practical payoffs. Study the ionosphere, improve communications, reduce uncertainty. If you're operating a global military, that matters. If you're running civilian infrastructure in a world tied together by timing signals and radio links, that matters too. One more point before we move on. The geography here is not an accident. Alaska sits under auroral activity like a front row seat at a space weather theater. If you want to observe how charged particles and magnetic fields sculpt the ionosphere, you go where the action happens. The University of Alaska Fairbanks brought that local expertise and long tradition of upper atmosphere research, making it a natural hub for the project. So, to sum up this origin story in plain terms, a Cold War push for technological superiority, decades of ionospheric curiosity driven by real-world needs, a coalition of military sponsors, a high-risk research funder, and a university with the right tools and location, and a mission aimed at making communication systems sturdier by understanding the wild, invisible ocean above our heads. Simple idea, big implications. Ready to see how the machinery actually works? Alright, now that we've set the stage, let's pull back the curtain on how HAARP actually works. Picture a vast open field in Alaska, but instead of crops, it's filled with towering metal antennas, all standing in perfect rows like a military formation. This isn't a radio station playing classic rock to the locals. This is an instrument designed to talk to the sky itself. The principle is straightforward in theory but powerful in practice. HAARP sends high-frequency radio waves straight up into the ionosphere. These aren't random blasts, they're finely tuned signals, targeted to stimulate a very small, controlled patch of that upper atmosphere. Think of it as tossing a pebble into a calm pond, not to make waves for fun, but to watch exactly how those ripples spread. Scientists call these perturbations, and by measuring them, they can map how the ionosphere behaves under different conditions. Now, the hardware. HAARP's antenna array is impressive. 180 antennas, covering 33 acres. That's a patch of land about the size of 25 football fields. Each antenna is like a musician in an orchestra, and they can all play in perfect sync. The magic is in the beam steering. By adjusting timing and phase, the signals can be focused like a spotlight or aimed in different directions without physically moving anything. This allows researchers to zero in on specific ionospheric regions or sweep across broader areas for mapping. But sending radio waves into the sky isn't just about poking it, it's also about heating it in a very controlled way. That's the controlled ionospheric heating part. When those high-frequency waves interact with the ionosphere, they can temporarily heat a targeted region by a few degrees. In human terms, that's nothing. But in the delicate balance of charged particles up there, even a small temperature shift can change electron density. And electron density is what determines how radio signals bend, bounce, or vanish entirely. By heating a small area, researchers can create conditions that mimic natural disturbances, then watch them in real time. The applications are where it gets interesting. This research supports GPS accuracy, and that means more than just finding the nearest coffee shop. GPS signals guide ships in narrow channels, coordinate search and rescue operations, and keep global financial systems synchronized to the microsecond. HAARP also helps improve satellite communication reliability, which is vital for both civilian networks and national security. And it contributes to auroral studies. Those shimmering northern lights aren't just pretty, they're visual evidence of massive space weather events that can disrupt technology worldwide. And here's something worth remembering: despite the myths, HAARP doesn't have the raw power to fry the atmosphere or control the weather. Its output is high for a research facility, yes, but minuscule compared to natural forces from the sun. The real power lies in the precision, the ability to create measurable, repeatable conditions that help scientists predict and adapt to nature's much larger tantrums. If you want a mental picture, think of a giant, invisible laboratory in the sky, with HAARP as the only way to open and close the door on command. Every experiment is a way to learn the rules of that lab, rules that have been playing with our technology, whether we notice or not. Now that you know how the system works, it's time to see what HAARP officially says it's doing with all this capability, and how it presents itself to the public. So, now that we've covered the mechanics, let's look at HAARP's official story, the narrative that's been put forward in public records, scientific papers, and outreach events. From the start, HAARP has emphasized that much of its research is not only legitimate but also transparent. One of the strongest pillars in their narrative is the existence of declassified research documentation. Over the years, multiple HAARP experiments have been made public, with detailed descriptions of their goals, their methods, and their results. You can actually find technical reports that outline when they ran certain heating experiments, what frequencies they used, and what changes they measured in the ionosphere. This level of detail is designed to show that there's nothing hidden in the basic scientific process. Then there's the publication record. HAARP's work hasn't just been kept in internal memos, it has made its way into peer-reviewed scientific journals. These papers cover topics like how radio waves propagate through the ionosphere, how disturbances affect communication systems, and how certain ionospheric patterns can be mapped with greater accuracy. Peer review is important here. It means that other experts in the field have looked at the methods and results, checked the math, and decided it's solid enough to be part of the public scientific record. But they don't just rely on journal articles to tell their story. HAARP has also made public outreach a key part of its image. They've hosted open house events where locals and visitors can tour the facility, ask questions, and even watch small demonstrations. This kind of direct contact is designed to counter the more sensational claims you might find online. Walking through the actual antenna array, talking to engineers, seeing the control room, it's a way of showing that it's a research station, not a doomsday machine. Another piece of the narrative is HAARP's integration into global research efforts. They've collaborated with universities and agencies around the world, contributing data, and participating in joint studies. That global network matters, because it spreads oversight across multiple institutions. If HAARP were doing something completely outside the bounds of accepted science, it would be harder to hide in a setting where international partners are involved in designing experiments and analyzing results. So, if you look at this from the official perspective, HAARP is positioned as an open, cooperative, scientifically rigorous facility. It produces declassified reports. It publishes in reputable journals. It opens its doors to the public. It works with the global scientific community. All of this is meant to reinforce a single point. This is a research project in plain sight, not a black box hidden away in Alaska's wilderness. But, and here's where it gets interesting, official narratives, even when true, don't necessarily erase public suspicion. In fact, sometimes they feed it, because the more an institution tries to project openness, the more some people wonder what's still behind the curtain. And that tension between public record and public perception is exactly where the next part of our story unfolds. Here's where the HAARP story takes a sharp turn. For some people, HAARP isn't just a research station, it's the source of global intrigue. And whether you believe the claims or not, these theories have shaped public perception in ways the official narrative never could. One of the most persistent allegations is that HAARP can manipulate the weather or even trigger seismic events. Critics claim that by heating the ionosphere, HAARP could theoretically redirect atmospheric currents, influencing storms, droughts, or hurricanes. In the more extreme versions, they say HAARP can induce earthquakes by somehow channeling energy into fault lines. Now, scientifically, the power levels involved just don't match the scale of those natural forces, but the point here isn't the physics, it's the perception. And perception often spreads faster than peer-reviewed papers. So where did these ideas take root? Timing is part of it. Many conspiracy theories sprouted after unusual events, strange weather patterns, seismic tremors in Alaska, or political unrest. When big events coincide with HAARP experiments, the human mind looks for connections. It's a natural psychological shortcut. This happened, that happened, therefore one caused the other. And once that seed is planted, it grows in fertile ground. The media and internet have been accelerants in this process. Sensational headlines, grainy YouTube videos, dramatic music under satellite images, they amplify fears beyond anything the facility's operators can control. Viral speculation thrives on mystery, and HAARP, with its remote location and high-tech arrays, is a perfect backdrop for that kind of storytelling. Even a routine maintenance shot of the antennas can be framed online as proof of secret experiments. And then there's the issue of trust, or rather, mistrust, in military-funded research. For many people, the fact that the US Air Force and Navy were central in HAARP's creation is enough to raise eyebrows. History offers plenty of examples where military programs weren't fully transparent with the public, and that legacy colors how new projects are seen. When oversight is opaque, when experiments are classified for any period of time, it's easy for the public to imagine hidden agendas, from covert surveillance systems to mind control experiments. It's worth noting that most of these claims can't be substantiated with credible evidence, but in the world of conspiracy theories, absence of proof is often spun as proof of a cover-up. And that's the real challenge. Once a narrative like this takes hold, it can persist for decades, regardless of what's actually happening on the ground. So, in the court of public opinion, HAARP exists in two worlds at once. In one, it's a scientific tool for studying the upper atmosphere. In the other, it's a mysterious and potentially dangerous weapon of global influence. And the more these two worlds talk past each other, the harder it becomes to bridge the gap. Now we step away from the rumors and look at something far more concrete, the structural realities of how HAARP operates, and what those realities can mean over time. At its core, HAARP is a military-origin research facility. That means decision-making power, funding, and oversight are all concentrated in a small number of institutions. When you have that level of centralization, you also inherit its risks. For one, the priorities of the funding agencies inevitably shape the direction of research. If the Navy or Air Force sees more strategic value in certain applications, those areas are likely to get more attention, even if broader scientific questions might be equally or more important. And then there's the issue of incentives. Military-led science is not immune to what economists call the mission creep. A project that begins with one set of objectives, say, studying ionospheric behavior for communications, can gradually expand its scope as new possibilities emerge. Each small shift feels justified internally, but years later, the project may be serving purposes its original architects never envisioned. The question is whether those shifts benefit the public or primarily serve the narrow goals of the institution in control. History shows us that when a system operates behind layers of classification, it can unintentionally erode trust. Even if the work being done is harmless or beneficial, the secrecy creates a vacuum, and vacuums get filled with suspicion. Once public confidence is shaken, it's very hard to rebuild. That mistrust doesn't just affect HAARP, it spills over into public perception of science as a whole. There's also a more subtle consequence. When research is centralized, the flow of information tends to be one way, from the inside out. This means outside experts, independent reviewers, or the general public have limited access to the raw data or the decision-making process. Without that transparency, it becomes almost impossible for external parties to verify claims or challenge assumptions in real time. And in science, challenges are not a nuisance. They're the mechanism that keeps the work honest. Think of it like a single lighthouse controlling all the signals in a busy shipping channel. If that one lighthouse changes its beam, all the ships adjust their course, whether or not the change is in their best interest. Centralization amplifies the influence of whoever holds the controls, for better or worse. And while HAARP's official uses may remain consistent, the potential for repurposing is always there. Technology is neutral, but the incentives behind its use are not. If those incentives shift, the technology often follows. That's the nature of centralized systems, and history gives us no shortage of examples where they've drifted far from their original intent. So the question isn't just whether HAARP is doing what it says today. It's also about whether the structure around it encourages accountability, or quietly enables shifts in purpose without meaningful public oversight. That's not conspiracy theory. That's simply understanding the natural behavior of centralized, incentive-driven systems. If centralization brings certain risks, then what might the opposite look like? This is where the idea of decentralized, open scientific collaboration comes into play, and it's not just a philosophical talking point. It's a model that has worked in other fields, and it's worth imagining how it could apply to something like HAARP's research. In a decentralized system, multiple facilities in different countries or regions could run similar experiments, share their results in real time, and openly compare findings. No single institution would have the authority to steer the entire direction of the work, and no one would have exclusive control over the data. This kind of structure doesn't eliminate disagreements, but it forces them into the open, where they can be debated and resolved in public view. Transparency is at the heart of this model. Imagine if all raw HAARP data, not just the polished reports, were streamed to an open database that universities, independent scientists, and even the general public could access. People could analyze the results themselves, replicate the experiments elsewhere, and either confirm or challenge the interpretations. Not only would this build trust, it would likely accelerate discoveries. After all, a wider network of minds often solves problems faster than a single closed group. We can look to examples like the Human Genome Project or certain areas of astrophysics, where scientists across the globe contribute to shared repositories and collaborate without centralized control over every detail. These efforts didn't just produce breakthroughs, they built credibility, because no one entity could quietly reshape the findings to fit a narrow agenda. Now, that doesn't mean decentralization is without challenges. Coordinating multiple facilities requires funding, logistical planning, and an agreed set of standards. And for research areas that intersect with national security, as ionospheric research sometimes does, there's always a tension between openness and protection of sensitive capabilities. But the fact that it's difficult doesn't mean it's impossible. There's also a human factor here. Openness changes incentives. In a closed system, your primary accountability is to the institution funding you. In an open system, your accountability extends to your peers, your competitors, and the public, all of whom can see, question, and critique your work. That pressure tends to filter out sloppy science and forces researchers to make stronger, more defensible claims. So, when we talk about decentralized alternatives, we're not talking about dismantling HAARP or abandoning ionospheric research. We're talking about embedding it in a larger network where no single entity owns the narrative, where the data speaks for itself, and where the public has more than just an official press release to go on. If nothing else, such a model could diffuse some of the suspicion that has followed HAARP for decades. Because while secrecy may be justified in certain cases, openness is often the best antidote to mistrust. And in a world where information spreads faster than ever, true or not, that trust can be the difference between public support and public skepticism. We've traveled from HAARP's Cold War origins, through its technical workings, to the official record, the public's doubts, and the deeper structural issues that shape how science is done. Now it's time to step back and look at the bigger picture, not just about HAARP, but about what it represents. At its core, HAARP sits in that complex intersection where science, technology, and military strategy meet. And whenever those worlds overlap, there's a balancing act between what is discovered and how it is used. The benefits are real: improved communication systems, better understanding of space weather, Insights that help protect both civilian and military infrastructure. But so are the costs when transparency is limited and control is centralized. The story of HAARP raises a set of questions that go beyond antennas in Alaska. How do we weigh the value of scientific discovery against the potential for its misuse? Who should decide which experiments are worth pursuing? And who should have access to their results? Can a project funded and guided by strategic interests ever fully earn public trust? Or does secrecy inevitably cast a shadow over the science? And maybe the most important question, if the knowledge gained from projects like this truly benefits everyone, why not design them from the ground up to be as open and collaborative as possible? In an era where data can move around the world in seconds, the barriers to openness are often less about technology and more about choice. The lesson here isn't just about one facility. It's about the systems we build to pursue knowledge, and how those systems either reinforce or erode trust over time. Centralized control can drive focus, but it can also narrow vision. Decentralized collaboration can spread knowledge, but it requires a willingness to share power. The way we choose between those paths will shape not just the future of atmospheric research, but the public's relationship with science itself. So as you think about HAARP, don't just think about the antennas or the heating experiments. Think about what it tells us about how we explore, who gets to decide, and what it means when knowledge is treated as both a public good and a guarded asset. If you've enjoyed this deep dive into the history, science, and implications of HAARP, make sure to like, comment, and subscribe so you don't miss future episodes. And if you want to explore even more stories about hidden history, overlooked events, and the forces that have shaped our world, check out my book History They Tried to Erase. You'll find the link in the description. For more thoughtful and entertaining history, stick around the channel. There's a lot more to uncover.